Hello friends, welcome to engineering tutorial. So we'll continue our discussion on thermodynamics, that is thermal properties of matter. So in this video we are going to discuss about thermal expansion of liquids, and we'll discuss another very interesting concept, which is the anomalous expansion of water, which will be related to the peculiar behavior in which uh, you know water behaves when it's heated from 0 degrees Celsius. Okay, so let's get started. So we have discussed thermal expansion of solids, where we discuss linear expansion, surface expansion and volume expansion. Now we'll discuss thermal expansion of liquids. So basically, in case of liquids and gases, we'll mostly be dealing with volume, the volumetric expansion or cubical expansion. Okay, this. So here, when it comes to liquids, there are two types of expansion which happens. Why? We'll discuss that. First one is apparent expansion, second one is real expansion. Okay, so let us try to understand that. So both of them happen in terms of volume, in terms of the volumetric expansion coefficient, which we know, that is the change in volume is directly proportional to the initial volume of the liquid and the change in temperature, that is final and initial minus initial temperature, and gamma is the volume expansion coefficient of that liquid. Everything stays the same, but here the situation is something like that. Let us say we have a given mass and volume of a liquid which is heated in a container. Okay, so the container is solid, so it has a certain volume expansion coefficient. So when the liquid in the container is heated, first the liquid that undergoes volume expansion, and also the container, that is the solid container, that also undergoes volume expansion. Okay, this is the thing. So here we have to take into account the expansion of the liquid and also the expansion of the container. So that's where the concept of apparent and real expansion come into play. So if we have to define them, express them in form of a formula or an expression, apparent expansion will be the apparent increase in volume of the liquid divided by the original volume and the rise in temperature. It is expressed as this: increase in volume, that is apparent volume, divided by initial volume. Let's say the initial volume is V0 and the change in temperature is represented by delta T. And real expansion is real increase in volume of liquid by original volume and rise in temperature. So the interesting relationship between apparent and real expansion is given by this, where the expansion of the container is also taken into consideration. That's why I said solid, the liquid is heated in a solid container. Both of them will undergo volume expansion. So in order to calculate the real expansion, how much the liquid has expanded, we have to take into consideration the volumetric expansion of the solid container also. So this is given by this, where the increase in the volume of the container, delta Vc, by the original volume of the container Vc into delta T. That is the coefficient of container expansion. Okay, so this is gamma A, coefficient of apparent expansion. gamma R, which is coefficient of real expansion. This is for the liquid, and this is for the container, gamma C, coefficient of volumetric expansion of the container. Okay, this, and the real volumetric expansion coefficient is equal to the coefficient of apparent increase in volume plus the coefficient of the volumetric expansion of the container. This, the sum of these two, apparent expansion plus container expansion, that gives us the real volumetric expansion coefficient of the liquid. This is the thing. Okay, this is the thing. So you have to understand it. If we find such a container, solid container, which does not expand with temperature, okay, which does not expand, in that case there would have been no need of apparent and real expansion. Both of them would have been the same thing. Real expansion would have been equal to apparent expansion, because there would be no such need to take these things into consideration. But here, since both of them are undergoing expansion, the liquid is also increasing volume, and also the container along with it is also increasing in volume. So in order to find out the real increase in volume of the liquid, we have to take into consideration the container expansion, volumetric expansion coefficient. So this is the formula. So here it is what I'm trying to say. Let us say this container, which contains a certain volume of liquid, it is heated. So suppose we design, for hypothetically, let us say that we design a container which does not expand on heating, a solid container which does not expand on heating. In that case, only the liquid in the container, it will undergo expansion, volumetric expansion, because the container does not expand. In that case, okay, in that case, there is no need of the concept of apparent expansion and real expansion, because both of them will be the same, because only the liquid in the container is undergoing change in volume. So directly we can measure the change in the volume of the liquid, because the volume of the container is constant. But actually in real situations, what happens, both the liquid and the container, they expand together. So in that case, the change in volume, if we only take the volume of the liquid into consideration, that will give us the wrong result, an error, because change in volume of the container also affects the increase or decrease, the measurement level of the increase in volume of the liquid. There will be an error, because the container is also expanding along with it. Okay, if we are measuring it through change in level of the liquid, the level will more or less stay the same. Okay, if we are measuring the volume of the liquid in terms of level, then the level will more or less stay the same. Okay, because the container is also expanding along with it. So in that case, we have to take into consideration both the volumetric expansion coefficient of the container, then the real expansion and apparent expansion, all three. Okay, and real is apparent plus container expansion. Okay, so this is the thing. Okay, now the second part, which is peculiar behavior of water, anomalous expansion of water. Now we know that liquids, like solids, they also expand when they are heated, and only we consider the volumetric expansion. But water, it behaves in a peculiar manner in the range of 0 degrees Celsius to 4 degrees Celsius, especially this point, the 4 degree Celsius point. So when water at 0 degrees Celsius is heated, okay, so here we have represented it in terms of a graph where we have a certain volume of 1 kg of water which is initially at temperature 0 degree Celsius. It is heated in a container, whatever it is heated. So if you see, when it is heated, it does not increase, it does not expand immediately. There is no increase in volume after heating, but in a peculiar way the volume starts decreasing, which is exhibited by this dip in the curve. Okay, so the volume starts decreasing up to this point, the 4 degree Celsius point, up to this 4 degree Celsius point. Now from this 4 degree Celsius point, when the temperature is increased from here, the volume starts increasing. Okay, beyond this 4 degree Celsius point, the volume starts to increase. This is the peculiar behavior of water. From 0 degrees Celsius to 4 degrees Celsius, the volume starts decreasing, and beyond 4 degrees Celsius, it starts increasing. Now, if we express it in terms of density and temperature, we know density is equal to mass by volume. Mass is remaining constant. So, in between the 0 degrees Celsius and 4 degrees Celsius point, as volume is decreasing, so obviously density will increase, and since at the 4 degrees Celsius point volume is minimum, okay, volume is minimum, so obviously density will be maximum at this point, the 4 degrees Celsius point, okay, which is this, which is expressed in kg per meter cube into 10 to the power 3, and here the volume is expressed for 1 kg of water, whatever the volume, into 10 to the power minus 3 meter cube, and temperature in Celsius. Okay, so this is the peculiar way in which water behaves when it is heated, especially in the 0 degrees Celsius to 4 degrees Celsius range. Okay, so the two important points is that volume of any mass of water, it is minimum at 4 degrees Celsius, and as a result of it density is maximum at 4 degree Celsius. Okay, that into this much, this unit. And this behavior of water is very much important for preservation of aquatic life, because when we go deep into the ocean during the change of seasons, because of this property, water does not freeze immediately from 0 degrees Celsius to 4 degrees Celsius. When there is fluctuation in temperature, there is no sudden change in density of the water, which results in preservation of aquatic life. Okay, so in this video we have discussed about thermal expansion of liquids, that is apparent and real expansion, which takes into consideration the volumetric expansion of the container in which the liquid is heated, and that's why the concept of apparent and real expansion they come into play, which is this. You can remember, real expansion is apparent expansion plus container expansion. This is the volumetric expansion coefficients gamma in terms of that. And when water is heated from 0 degrees Celsius, in the range of 0 degrees Celsius to 4 degrees Celsius, volume decreases, volume being minimum at 4 degrees Celsius, and beyond that point it starts increasing, and as a result density is maximum at 1. So from 0 degree Celsius, density of water starts increasing, and then beyond it, it starts decreasing. Okay, so this is the concept of anomalous expansion of water. Okay,